workshop. And our first speaker is Professor Leonid Mytnik from Technion, and he's going to speak on pathwise uniqueness for stochastic heat equations with Hölder continuous coefficients. Yeah.
Okay, first of all, I'd like to thank the organizers for inviting me to this beautiful place, to this workshop. I really enjoying it. And I'm going to talk about the uniqueness for stochastic heat equation with non-Lipschitz coefficients. So the equation is very simple. It's a heat equation perturbed by multiplicative noise, and this is formal way of writing it, but the more precise way, the precise way is to write it as a mild solution of this equation, where we have the convolution of the initial conditions with the heat kernel, with the Gaussian kernel, and also convolution of this part with the Gaussian kernel, with the Gaussian density. We'll consider a number of cases. So we'll be talking about W being Gaussian noise, and it will be always white in time, which means the correlation is given in time by delta. And in space, it may be colored or white, depending on k. If k is a delta function, which is the most interesting case, then the noise will be also white in the spatial parameter. So this is the equation we're dealing with, and so that just to remind the people, there are two types of basically two types of uniqueness people are talking about. The pathwise uniqueness, which means we fix the noise, and any two solutions should coincide almost surely. And there is a so-called law, Untitled law, or weak uniqueness. If you define any two solutions of such equation, they may be defined for different driving noises, even in different probability spaces, but the law of two solutions should coincide. Then this is called weak uniqueness, and so weak follows from the pathwise. But this basically are two types, and we mostly will be talking about the pathwise uniqueness for the heat equation. It's known, for example, that if W is the space-time white noise, which correlation in time is space is delta, also delta, then the functional value solution exists only in dimension 1. And what about uniqueness? If sigma is Lipschitz function, then pathwise uniqueness follows easily. If it's not, then in most of it's a kind of question we're trying to address. We'll be addressing in this talk. And just to relate it to the talk of to the morning talk of Professor Fandoli, so we are doing something different here. We somehow in the absence of noise, we have a very good equation, and the heat equation definitely has a unique solution. But when we add this noise, then the non-Lipschitz coefficient sigma may create non-unique situation. So it's the other direction. So we perturb something which has unique solution and get something that maybe not well posed. One of the questions one may ask is whether it's an interesting case. Maybe most of the interesting examples come with Lipschitz coefficients, but the answer is no. From branching particle systems, we often naturally get the example of the SPDEs with non-Lipschitz coefficient sigma, and the one of the most prominent example is the super Brownian motion, which is the limit of branching Brownian motions. The process can be built as a limit of such process in the following way. You take about n particles in RD of order n particles, and you take very fast branching rate. Every time 1 over n there is splitting with probability 1/2 or dying probability 1/2, which means this is a critical branching. And new particles in the generation you move as independent Brownian motion again. You define the empirical measure of the particles xn, and this is the measure valued process. And as n goes to infinity, this process converges to measure valued process, which is called super Brownian motion. And what do we know about this process? If dimension of the space where the Brownian motions were living, the particles were living, is greater than 1, then the measure is single with respect to Lebesgue measure. The measure valued process, the measures that you get, they are singular with respect to Lebesgue measure. If dimension is 1, then there is a density. So for any time t, there is a density xtx, and this density, it was proved more than 20 years ago now. It satisfies the following simple stochastic heat equation, where we have this heat terminal that we always have, and we have this square root of x. So you have this non-Lipschitz coefficient sigma, which happens to be square root of x, and w is again space-time white noise. So you can very naturally get these examples, and it's typical to get them such nonlinearities from branching particle systems. And you may ask what happens whether the solution to this unique, since it would be very bad if even for such basic example we don't know uniqueness, and that in fact we do know uniqueness in law for this equation. It follows by kind of very nice duality trick, which says that the Laplace transform of the solution to, or any solution of this equation, Laplace transform can be obtained as via solution of some nonlinear PDE, which has unique solution, and means that there is, since Laplace transform defines the distribution, then we know that there is unique and law solution to this SPD. So this is we know. So we know that at least in law the limit does unique, but we still don't know anything about the pathwise uniqueness. And in a sense, it's important question, since if I a bit change the model and make somehow the rate of branching dependent on the measure and get or on the density of particles in regions, then I may get here something which is not square root of x and a little bit more complicated function, suppose, but still in the class of Hölder continuous functions with some parameter, let's say greater than 1/2. So, but it won't be so nice like square root of x, and for most of the examples, the duality doesn't work. So, and we don't know whether the solution is unique or not, and as a result, we don't know whether the limiting object somehow depends on the approximation we built, which is kind of very non-convenient. So the weak uniqueness in this setting usually which usually is proved by in many cases proved the duality method is very non-robust method of and in many cases it just doesn't work. We don't know the right duality function, and we don't know uniqueness. And so the question we ask, first of all, is there any chance to get pathwise pathwise uniqueness in the case of non-Lipschitz coefficient. And here we just go back to the more familiar ground, the SDEs. If you take a very simple SDE, dx is sigma x dB, where b is one-dimensional Brownian motion, then there is all the result of Yamada Watanabe, which says that if sigma is Hölder continuous with exponent 1/2, then there is pathwise uniqueness. Which means situation here is much better than situation in the case of deterministic ODEs, and this results one can make formulate a bit stronger, but pretty much sharp. If there are counterexamples for sigma which Hölder continuous with count less than 1/2, and one can construct a number of solutions. So I just give you the short proof of this Yamada Watanabe result, since most of the attempts to prove pathwise uniqueness for SPDEs were somehow based on imitation of that proof. Many of them failed, and in fact we'll try to imitate the proof, and we'll see how we can do better job here. So the proof in fact is very nice and simple. You take the sequence of functions phi n which converge to absolute value function such that the second derivative converges to the delta function, and usually proof of pathwise uniqueness, you take two solutions, take the difference, and try to show that the difference is 0. It's kind of what you want to do. So we take this x tilde, which is difference of two solutions, which satisfies this equation, sigma x1 minus x2. Here is supposedly sigma of x2, I guess. Yeah, sorry. dB. And then you apply function phi n to this difference x tilde and write the eta formula. In eta formula, we have two terms. This is a martingale. One term is a martingale. We don't care about martingale. And the other term is the correction term, which comes from the eta terminal, which comes from the quadratic variation of this martingale. Okay, and here is the second derivative of phi. So we want to show that this guy will converge to the absolute value of x tilde. So let's take the absolute expectation on both sides. This is martingale, so it gives you 0. So you have this expected value of the left-hand side and the expected value of this side. Sigma is Hölder with 1/2, but you gain another square here, since this comes from quadratic variation. So you get that this difference squared is bounded by absolute value of x tilde, and you have this guy which converges to the delta function. So this times this goes to 0. This is the whole proof. So it's in fact very simple and nice. And 1/2 is the smallest power that you can do this trick, since if it's less than 1/2, you have less than 1 here, and it's not necessarily goes to 0. It's 1/2. So it's a nice, simple 3 lines proof. So there is a chance to have uniqueness for SPDEs. What the situation is that, for example, for this SPDE for super Brownian motion, for density of super Brownian motion, dimension 1, it's still not known. So we still don't know. Since here you have the same this critical 1/2 that we had in the Yamada Watanabe theorem. No, at this point nobody knows where the pathwise uniqueness holds for solution of this equation. And we'll talk about the general equation, where sigma is Hölder continuous exponent gamma, and we are interested in conditions on gamma such that the pathwise uniqueness holds. Okay, we know that when we are in the situation in the Yamada Watanabe setting of one-dimensional SDE, the critical gamma is 1/2. Okay, turns out that in the case of this stochastic heat equation, the critical gamma we were able to prove in the joint work with Ed Perkins was 3/4. So we were able to show that for any sigma which is Hölder continuous with exponent greater than 3/4, there is a pathwise uniqueness for W being a space-time white noise, which is kind of halfway to a half, but we still don't know whether maybe it's a final stop is 3/4. It's not clear. Okay, so I won't give you immediately the proof of this result. I give you some ideas and somehow show the history how we arrived to the how the right to ideas that led eventually to the proof of this result. So it started several years ago, where we didn't have a clue how to proceed with this equation driven by space-time white noise, and in a joint work with Ed and Anya Sturm, we decided to consider the less singular noise, less singular in space. Since the idea and the intuition somehow said that the less singular noise in space you take, the more chances for uniqueness you have. For example, if you take W just to be one Brownian motion, you are more or less in the Yamada-Watanabe setting, and you somehow can pretty much easily prove that the critical exponent is 1/2. So the idea was to take something between this one Brownian motion and space-time white noise, and to see if we can see gain some ideas there from this consideration. So so we start from this equation, as I said, the one driven by less singular noise. So in this setting, I take W to be white in time as before, and colored in space such that K x minus y is the correlation kernel. And on this correlation kernel, we have these assumptions. It has pole at 0, and the exponent of the pole is alpha. Okay, and sigma again is Hölder continuous exponent gamma. Just few words about existence of function valued solution. For alpha less than 2 minimum d, this existence was proved in a number of papers by Zabchik, Dalan, and it was proved for Lipschitz case, but existent proofs easily can be transformed to the non-Lipschitz situations. So for existence, Lipschitz condition is not essential. It's essential for proving uniqueness. So just to remind you, so keep in mind that alpha cannot be greater than 2. So alpha is less than 2 minimum d. So we are in this, always in this situation. And another remark. So somehow, why did you want to do it this way? We somehow felt that if you, for example, dimension 1, and you take alpha going to 1, then you converge to the case of white noise. Since alpha equals to 1 somehow corresponds to the situation with driving white noise in time and space, and alpha equals to 0 corresponds to the SD, one-dimensional SD. So this was the idea, and the result said something like not something, just said exactly what is here, that pathwise uniqueness for that equation holds for alpha less than 2 gamma minus 1. Okay, and just in the remark, if you want to read something about the white noise case, you read nothing, since you take d equals 1, alpha equals 1, and you get that gamma should be greater than 1, which is nonsense, since gamma equals 1 Lipschitz. I know without any theorem that it will be, the solution will be unique whenever there is sense to this equation. Okay, which means it somehow indicates one of two possible situations, or this is non-optimal, or maybe there is no pathwise uniqueness. So but this was the first result in that direction, that at least we get something. When alpha is less than 1, we get some pathwise uniqueness results for non-Lipschitz for non-Lipschitz, for SPDE with non-Lipschitz coefficient, and noise with singular correlation. It's not as singular as white noise, but it was still singular. Okay. Yeah, the proof. So I'll talk about the proof of this result, since it's important. In a sense, it's it gives most of the ideas of how the latest result was proved about the white noise-driven equation. Okay, so what we are trying to do, we are trying to imitate the Yamada-Watanabe proof. We are trying to do the same. Take two solutions, x1, x2, takes the difference, and the difference satisfies this equation. Yeah, sigma x1 minus sigma x2. Okay. Now, what we did in Yamada-Watanabe proof, we took the sequence of functions, fn, phi n, fn. No, phi n. Phi n was conversion to the absolute value function, and second derivative was conversion to delta function. So what I would probably would do in the Yamada-Watanabe case, I would try to take phi n of x tilde tx. Okay, but there is one problem. X tilde tx is not a semi-martingale in the case of SPDE. Yeah, it's in the case of SDE, for any fixed point in space, for the case of SDE, when you take the process, the semi-martingale and apply eta formula. When you take the SPDE with singular driving noise, then this guy is not necessarily a semi-martingale. So what should you do to make it a semi-martingale? You should take some smooth function, integrate this x tilde against this smooth function, and then the process will be a semi-martingale, and then you will be able to apply the formula. This is how it works. Yeah? So what we are doing, we take x tilde, take some function f and x that will eventually go to the delta function at x. So this process is a semi-martingale. We can apply phi n, and we can apply eta formula. Okay? This goes to delta function, this goes to the absolute value function, this goes to the absolute value of x tilde. Okay, this is the same what we have been done in Yamada-Watanabe proof, with only difference that I have to integrate this solution with respect to something which approximates delta function. And the hope is that the right-hand side will go to 0. Okay. Now, I won't reproduce what is on the right-hand side, since it's too long and it somehow depresses me when I will write it on the slide. It's 3 lines or 4 lines. One thing one should understand, that this guy doesn't create a problem. Whatever comes from that guy is not a problem, since it's a Laplacian. So this guy on the right-hand side will be okay. It won't create a problem. What creates the problem? The guy that comes from the quadratic variation of this martingale. So the only thing you have to control is the guy that comes from the quadratic variation of the martingale corresponding to this, which will be on the right-hand side. If you control that guy, then we can show that it goes to 0. Then we can finish the proof. So yeah, this is the guy which is supposed to be the on the right-hand side, which comes from the quadratic variation of the martingale. There are several things here. Okay, so first of all, this part. Okay, this is the second derivative of something which converges to the absolute value of x tilde sx. Yeah, whatever was in the Yamada-Watanabe case, more or less the same. Okay, then you have x tilde z to the gamma, x tilde sy to the gamma, and these are approximate delta function, which converge to a delta function at x. And this is the correlation kernel. Okay. Now, if we're in the case which corresponds to the case of ordinary SDE, this k is just a constant, just 1, take 1. Okay? Which means that this will converge to delta, this will converge to delta, we have double integral here, this will converge to x tilde s at the point x to the gamma, x tilde s at the point x to the gamma. This will give you power 2 gamma. Okay? To give you 2 gamma, this converts to a delta function. Remember, delta function something to the power 1 is enough to have uniqueness for this guy to converge to 0. So which means if gamma is greater or equal than 1/2, we are still in business if this k is constant. Okay, it's just the Yamada-Watanabe, the same argument. Where the trouble starts, when k has a pole at 0. Since when k has a pole at 0, this converges to delta function, this guy converges to infinity. Okay, which means, and this converges to the delta function at 0. Yeah? So, so what does it mean? This part will go to 0. This part will go to infinity. So we have some price to pay for the singularity of correlation kernel. Okay. And here is the, so what, in fact, this was why why all the attempts to prove it before failed, since people didn't know what to do with this term, okay, how to handle it. But when you take a look at this, then in some sense you understand, you realize the following, that what's going on here, you have, when n goes to infinity, you take a look at this difference of two solutions. What matters is only behavior of the solution close to the difference of two solutions close to the point where it equals to 0. So since what matters, suppose there is some point x and x tilde sx equals to 0 here. Okay? Now, xsz and xsy, they are not at 0 yet. They are close to this x. Yeah, since the only way to get non-trivial limit of this expression, since phi double prime n is a delta function at 0, the only way to get non-trivial limit is at the points where x tilde sx is 0. But x tilde sx is 0, x tilde sz, x tilde sy still not. Okay, but they are close, and solution is continuous. So what you have to control, and you know the window, since you know how fast fn converges to the delta function. So the only thing you need to control the behavior of x tilde in the neighborhood of the points where it's 0. How far it can be away of 0. Which in a sense, which means, in fact, you need to know the Hölder continuity index of x tilde. If you know the Hölder continuity of x tilde near the points where it's 0, then you can control how big this guy can be for each n, and hope when n goes to infinity, you can compensate this infinity. That's the idea. So the only thing one should really know is the Hölder continuity of this guy. That's what we thought, and that's what I said. Crucial thing is Hölder continuity of x tilde s at x. Okay? And suppose you know the Hölder continuity index. Suppose you know that it's the xi. Then one can show that this guy converges to 0 if this relation holds. Okay, it's kind of relation between how strong is this singularity and how and the index of Hölder index of continuity. Or if you write it in the other way, you get gamma greater 1/2 plus alpha over 2 sigma. Okay, so what you see here is what you expect to see. This is the price you pay for having a singular noise. Okay, the stronger singularity alpha, the higher price you pay. If there is no singularity, just 1/2 like Yamada-Watanabe. If there is singularity, then you go up. The better regularity of the x tilde at the point where it's 0, the less price you pay. High xi, the smaller critical gamma you can take. This is a trade-off of singularity and of the strength of singularity alpha and the Hölder continuity xi. It's clear that the index Hölder continuity xi depends on singularity of the noise. Since the more singular the more singular noise spatially, then worse singularity you have. Since if you take if you take alpha equals to 0, then you can have then it will be very smooth solution. If you have heat equation, just one running Brownian motion. Okay, and so this is the condition that we had, and so in fact the task was to run for known results for SPDE driven by colored noise, and thanks to Marta and Sarah, we did have the result. We did know how the Hölder continuity depends on the singularity of the noise alpha. This was the result. The result that for any xi less than 1 minus alpha over 2, still there is Hölder continuous with this xi. So you can just take this, substitute here, solve, and you will get this. Yeah, when you try to somehow check with the situation that you do know, and you start obtaining nonsense, since you take gamma goes to 1, which is the Lipschitz situation, and you get that you can handle only alpha less than 2/3, okay, which is bad, since even in dimension 1, I should be able to handle up to alpha equals 1. This is where my alpha should be. If gamma goes to 1, it's the Lipschitz situation. I should be able to control up to alpha, which means something is non-optimal in what we are doing. And this, what was non-optimal thing was the following. When in this picture, I told you we have to control the Hölder continuity of x tilde near the points where x tilde is 0. Let's take points where x tilde is 0. Okay? But at the points where x tilde is this result says Hölder continuity at any point. At the point where x tilde is 0, the noise is very small. Yeah? Why the noise is very small? If you take this equation, oh, what's this? How could it back? If you take this equation, yeah, if the difference is small, then this guy is small, which means that at the points where x tilde is small, you have much better regularity of the solution. Yeah, this is the only thing one should have realized, that for any points, okay, you know that it cannot be worse than 1 minus alpha over 2, but at the points where x tilde is small, it might be much better. And this was exactly the case. We proved that at the points where x tilde is 0, x tilde is psi Hölder continuous with this index, with this upper bound for the index. Which means that if alpha is less than 2 gamma minus 1, this guy is greater than 1, which in fact means that psi is almost Lipschitz. The x tilde is almost Lipschitz at these points, which is much better than 1 minus alpha over 2. Okay? And this is the corollary at points where you see x tilde is psi Hölder continuous. Okay, to be precise, we didn't prove exactly this, but we proved the result very, very close to what is written. We proved somehow that in the neighborhood of these points, some deviations the increments can be larger than something, but it's morally this is the result. And just another remark that Murray and Tribe long ago had the result similar to this one. They just didn't publish it in the case of white noise. So which means that if this happens psi less than 1, and I remind you the condition, this was the condition for pathwise uniqueness, so we just put psi here and you get for alpha less than 2 gamma minus 1, the pathwise uniqueness holds. You just need to know what is the xi. If you know the xi, you get the condition on alpha. And this finishes that proof. Okay? And now immediately arise the question, okay, it's not that bad as before. When gamma goes to 1, you get alpha less than 1. So which doesn't sound like that crazy as 2/3. But still, we're in trouble, since I remind you that alpha could go up to 2 if dimension is greater than 1. Okay? And here, this result doesn't depend on dimension. And if gamma goes to 1, alpha goes just to 1, which means in dimension 2, we are still non-optimal. Which brings again the question, what's wrong in what we are doing? What's not optimal in what we are doing? And so it's bring the question of optimality. As I said, it's okay. First of all, alpha d equals 1 is not good, and d equals 2 is even worse. So, and what is non-optimal in what we are doing? So you see, this is the result on Hölder continuity that we got at the points where x tilde is 0. And you see that there is annoying minimum 1 here, which means that, okay, which means you can't have Hölder index greater than 1. Okay? But somehow this minimum 1 suggests that if this part is greater than 1, you just have better control of regularity of x tilde in these points. Yeah? Which means you have expansion of the function near this point, not just the first term in Taylor section, in Taylor expansion, but maybe just the second, also the second term or another term. Or in other words, you may have control, or in some sense control of the regularity of the derivative, if you want. If there is derivative. But in a sense, this is just expansion of the polynomial expansion of x tilde near the points where x tilde is 0. So in this minimum suggests that if this guy is greater than 1, you have more than the first term. And this is exactly what if you do formal calculations, you just say, okay, let's forget about minimum 1, and suppose xi can be this. Then you do the calculations for pathwise uniqueness, substitute whatever you have to substitute, and you get this condition. Instead of alpha less than 2 gamma minus 1, you get alpha less than 2 times 2 gamma minus 1, which is much better. Which means when gamma goes to 1, you go up to 2. Alpha goes up to 2. Or in terms of gamma, you get this condition. And for alpha equals to 1, which means white case in dimension 1, you get gamma greater than 3/4, which was exactly the result we claimed with Perkins. Yeah? So the only problem is to make sense of all this calculation for more than one page, since it gives you intuition, okay, the result might be true, but you need to, in fact, to show that the solution here, you can really control the behavioral solution near the points where it's 0. And this is exactly what we did, and this was exactly the proof. So to show that you can control the behavior of the solution. Okay. Now I don't say more about the proof of the theorem, since I just want to say that the idea is here, and all the rest is just brute force calculation, which in a sense requires to check the regularity, how a regular solution near this point. The question what arises is the following: whether 3/4 is optimal. Which means if we believe that we did the best here, the best that we could, then it might be possible to construct a counterexample to counterexample, which says that for gamma less than 3/4, you can construct some equation with non-unique solution, two solutions to the same equation. This is not finished yet. It's a work in progress which we are doing together with Ed and Carl, and using the calculation we did many years ago with Martin Barlow. Well, the idea is, if you do believe that's optimal, you should be able to construct a counterexample. Now the question is how the counterexample might work. How you could try to construct two solutions to this equation starting. Okay, one is clear, it's 0. Now we need the second one. And the idea is to construct this guy x as difference of two positive solutions. Okay, I want one positive solution to this equation, one negative, and somehow difference between them should solve this equation. It shouldn't be trivial. And it comes from something we did, we tried to do about 10 years ago, yes, which is called the hard-killing model. And hard-killing model, yeah, forget which button to have. Looks like this. Okay, you have two populations, x1 and x2, and each of them solves this equation. Okay, you have the same guy you had before. This is the Laplacian guy. You have this x to the gamma. Now there is no absolute value, so it's a positive guy. Some white noise. Now you have something which kills you. Yeah, just by a second. It's in dimension 1. I probably forgot to say this. Everything in dimension 1. You have something which kills you, and this term is the same for both populations. And there is immigration of mass. Okay, immigration of mass, which some deterministic mass coming in. In the regular case, you may just take some mass at time 0. This is immigration of mass. But we allow ourselves to have immigration which is continuous in time. That mass always is popping, coming into the equation. Okay, so what does it mean? One can think about this in terms of some particle systems. Okay, for each population, you have some equation which describes the evolution, some kind of branching evolution of particle systems. But what you require from them, that they don't live in the same place. This means x1 times x2 is always 0. Okay. So in terms of particles, it means if you describe evolution of two particles meet, then they annihilate each other. They annihilate each other immediately. That's why it's called hard-killing model, which means they don't wait some exponential time, whatever, when they are together. They just, when they meet, they kill each other. Okay? Which means that in the limit, if you go to say any kind of limit you want, you have, suppose this population x1, and this will be population x2. Okay, suppose this I call plus, this I call minus. So, and they don't live in the same place. They live in different places. Okay, and you can construct this. This you can construct. You don't know whether it's unique or not, but you can construct this system of two SPDEs. Okay, the characteristic feature, and this is minus delta A delta T. It's what happens here, since these guys have to kill each other. Okay, so it's at the interface of two populations. Okay, so this is what you want to construct. Now it's clear that if the immigration of the mass is the same for both populations, then difference of these two populations solves this equation. Yeah, since if you take the difference, this term cancels out, and if immigration term is the same, then it also cancels out, and you are left with this equation. Okay, this is crucial. You have two processes, and you somehow push the immigration, make the same immigration for both of them. Okay. Again, the trivial solution of this will be you have two immigrations, they kill each other immediately, and each population is 0 for all the time. Yeah, it's the trivial solution to this problem. You have two populations, they immigrate here, it's the same, they kill each other immediately, so it's 0. The question is, can you construct something non-trivial. And the idea is to try to construct it by some approximation. I want to construct the immigration, which in the beginning is different on the approximation level. But when epsilon goes to 0, whatever will be there, then immigration for each population converges to the same immigration. Okay, that's the idea. How we can construct different immigrations that will converge to the same? I'll take two Poisson random measures with high intensity and small atom of the jump, such that the intensity is the same when intensity. Such that in the limit they converge to the same migration. What the hell is this? Oh, it's over. I don't know the answer.
Maybe it was not switched on. Battery.
Press the button.
Which one? There are too many.
The flashing button.
Wow, miracle. Okay. Okay, so you have two independent Poisson random measures with intensity in time and in space. Okay, I'll probably try to write it. I have to draw a picture. So time goes in this direction. And we have an immigration of mass. You have Poisson point process with intensity epsilon mi delta t delta x here. So you have masses coming in. This is the immigration of the mass to each equation. Okay? And they're independent. This is for, let's say, for x1. And this is, say, for x2. My mass of each guy is epsilon, which means the total order of mass coming in is 1. Okay? So they come differently. It's clear that when we go to the limit of huge intensity of Poisson point process with small mass, each of the immigration goes to the same immigration, which is the Lebesgue measure on this strip in space and time. Okay? So they're going to the same, and it means that, in fact, the difference of two populations, x1 minus x2, converges to this process that you want to construct. Okay? Now, the question is whether the limit of these guys is trivial or not. Okay? Since what may happen is that whenever there are a lot of them, they are close to each other and they kill eventually each other. And the other scenario is that, let's say, one of them survives and is strong enough to kill all the other guys. If this is the scenario, then you construct non-trivial solution. If they kill each other, the only solution is trivial. Okay? Now, we'd like to work to show that if gamma is less than 3/4, then in fact there is non-trivial solution in the limit. That the limit of these guys is non-trivial. Okay. Okay. Now you can think about this. All the process I can construct in a sense in the discrete level as sum of many clusters. I don't write equation for the cluster, but in fact what you have. This is the migration of mass. From here, mass starting to propagate. This is a migration of the, say, negative mass. From here, they start to propagate. And they interact. They kill each other. When they meet, they annihilate each other. This is the situation. Each of these guys, which starts from this, I call a cluster. Okay, so you have epsilon minus 1 clusters in the epsilon minus 1 clusters in average. Okay, many of them, most of them live short time, but there are some of them that live long time. Okay, for example, if they are not killing each other, then you are talking more or less about some kind of branching system with interaction. So you have some mass coming in, there are a lot of them, most of them die very fast, but some of them survive. And one can show that if there is no killing, then there is a positive probability that there exists always a cluster which survives long time. Yeah, that you started somewhere here, and it lives for some time which is strictly positive. There is some bound from below. This is what's written here. Okay, there is if there is no killing, you can find a cluster that survives. So let's consider this situation. Let's consider some cluster, and suppose I shift the time in a way that I start my cluster here. This is what is supposed to be one of the surviving clusters in the absence of killing. Now we'll try to kill this cluster. Okay. What can kill this cluster? These blue guys. Okay. How they can kill it? There are two ways, more or less, to kill this cluster. One way, okay, I just I shifted time and position, so which means that there are some guys which may be born here. Yeah, there are some guys that may be born here, some guys may be born here. So this is a cluster. Okay, so if this cluster is born in the place which is covered by the blue guy, it's dead. It's immediately dead. Why? Since in the limit when epsilon goes to 0, this cluster starts from 0 mass. It's kind of you try to start the excursion of the process, and you start from 0. You escape from 0. So you start from 0 mass, which means that if there is some positive mass of the other population here, it kills this guy. Okay, this is one possibility. The other possibility is there are a lot of masses here, and they just kill it since there are more blue guys here than the mass of the white one. Okay, now let's consider. And so the question is how this can happen. How this blue guy can kill you. Okay, the option is they should be born in some place here and come to this place, so to have a non-trivial mass at this point, at the place of the birth of the white cluster. Okay, now the critical estimate is where they could be born. Each such particle, each mass propagates at the scale of Brownian motion, which means it cannot be born here and survive up to here. It should be in some parabola. And most of the clusters, they live short time. So what one can show that one cannot have the mass which is born here and surviving to this point. Which means if you have some point, it's almost surely not covered by the mass of the other clusters born before that time. This is the message. Okay, for gamma less than 3/4. Okay, and which means, so in a sense, this means the following: I take any point in the space, and I take the other process with immigration. the second process. And I ask whether this point is covered by the mass of the guys that were born before. And the answer is no, if gamma is greater than 3/4. The second question, what is the mass of guys that were born here? Again, the guys that were born, that live here, they're again in the parabola. So the mass of the guys, if this is parabola, let's say this is square root of t. Then the mass of guys which are born here is t to the 3/2. Yeah, you have t in time and square root of t here, t to the 3/2. Now, if you can show that the mass of the surviving cluster is greater than t to the 3/2, then you're in business, which means that the mass of white guy is greater than the mass of the blue guys in these points. And this is what you can easily show. You can show how big is the cluster which survives from this point. In fact, I guess I have it somewhere. Yeah, it's killing by cluster born after time 0. So this is the mass of the surviving cluster. It's 1/2 t to the 1/2 plus 1 or 4 1 minus gamma. And you see that if gamma is less than 3/4, this power is less than 3/2, which means this mass is greater than this mass, which means that the white guy wins the situation, wins the competition with the blue guys. Okay, it means that you can construct in the limit two separate populations such that the difference between them goes as a solution of the stochastic heat equation starting from 0 initial condition. And the last remark, so in the end what you have in this limit, if gamma less than 3/4, then you may construct solutions such that in many places of your state space there are guys that are born. So they are born in some places the white guys born, some places blue guys, and you have signed equation which goes from which goes like that. And we still don't have theorem. We're pretty much sure that the intuition here is well, 50% sure that intuition is correct. We can show for gamma less or equal than 1/2, the argument is precise, and for gamma between 1/2 and 3/4, it looks like it could be closed if one uses the intuition like that. Okay, many thanks for your attention.
Questions? Remarks?
And the uniqueness of positive solutions would be another.
Yeah, we don't know. This we construct only science solution. We don't know about it.
Any more? If not, can we thank Leonid for a beautiful talk? So we reconvene at 1:30.